regarding the posterior distribution, i.e. the density of the latent variables condition on the data and the parameters. And here we can apply, for example, expectation maximization to find these optimal theta. Here you iteratively try to find parameters, making the posterior and the likelihood as probabilistically congruent as possible. Nonetheless, the posterior must be known in this case, and the optimization can be intractable or slow and not scale well to high-dimensional data. What is the solution? Well, we can introduce further approximations, such as in variational inference. In VI, one approximate the posterior distribution by a family of distributions, denoted Q5 of Z. One can find these parameters by minimizing the Kullback-Leibler divergence between the approximate posterior and the true posterior. And the Kullback-Leibler divergence is a non-negative, non-symmetric metric that will convey how similar to probability distributions are. And by optimizing and iteratively updating these parameters, we can reduce the Kullback-Leibler divergence and attain a convergence from our approximate posterior to the true distribution. Nonetheless, there might not be closed-form expressions for these phi, and the scheme may thus be intractable. But to the rescue, we have Autoencoding Variational Base, written by Kingma and Welling. A quote from the original article states that the algorithm OEVB is a stochastic variational inference and learning algorithm that scales well to large data sets and may even work in the intractable case. So for our large data set, where we might have intractabilities, this is an algorithm we can use. And by OEVB, we can thus find the approximate posterior distribution and the data likelihood. So let's initiate with some autoencoder basics before we move into the algorithm. Here is a simple visualization of an autoencoder, where you input some data x, you map that with the deterministic function f to a code or a latent representation set, and you can then re-attain a reconstruction of your input with the deterministic mapping g, which is the decoder. So it's comprised of an encoder and a decoder function, and these are essentially two feed-forward neural networks. And the purpose of inputting data and then reconstructing it might appear quite odd. What we seek, however, is that the latent representation and code set here, that is usually in a lower dimension, will have some salient features of your input data. So we can use this in feature extraction and dimensionality reduction before other types of inference. So I suppose you know what this is, but for those of you who are new to this, a feed-forward neural network could look like this. So there is a simple, fully connected feed-forward neural network with 3 hidden layers. And it's essentially a directed acyclic graph with the topological sorting from the start of the graph to later in the sequence. And these are sometimes referred to as universal approximators, since they can virtually approximate any given function. And in each neuron in this network, a neuron transformation occurs, where the inputs are weighted, summed with a node bias, pushed through the activation function, and thence the output of each node in the network is rendered. Let's now extend this to the variational autoencoder. We can visualize this in the following manner. So you see it's quite similar, but instead here of having a deterministic mapping, we have some kind of probability distribution, and equaling here. So this is a stochastic generalization of the autoencoder, comprised of the encoding distribution from your input data to the latent representation, and a decoding distribution from your latent representation to the reconstruction of your input. And in addition to the feature extracting ability of the autoencoder, you here have generative abilities, which entails that you can put a new set through this network and attain an artificial sample x tilde. So, casting our original problem into this framework, suppose we have this data that is potentially high dimensional or from a complicated distribution. And we introduce latent variables Zn equaling each of these data points. Then we can let a generative process be characterized by draws from a prior distribution that we then can condition on and draw data points xn from a data likelihood. In a graphical model, it will have the following appearance. So you have some parameters data governing a process where latent variables give rise to data points xn. Now suppose we approximate the true posterior, such as in variational inference. So we let the posterior be approximated by q phi here. Then we can find optimal parameters phi and theta from the likelihood by maximizing an entity called the evidence lower bound. And this is essentially a metric conveying how probabilistically congruent your parameters and latent variables are to your observed data. And it's related to the evidence. So it's given by the following metric. You have the cross entropy between the approximate prior and posterior distribution and your log likelihood, and you have the Kullback-Leibler divergence between your approximate posterior and your prior distribution. Let's denote this metric LVAE. This is analogous to minimizing the Kullback-Leibler divergence between the approximate posterior and the true posterior. Here, however, you see that the log evidence is included in the end here of the metric, and this is intractable. So that's why we focus on the elbow instead when deriving these parameters. So the optimization and approximate inference can be applied with neural networks parameterizing the distributions. And what does this entail? Well, you input some data to a neural network, and that neural network will yield parameters to a probability distribution. So that's what it entails. So suppose the following holds. We have an isotropic-centered Gaussian prior. We let both likelihood and approximate posterior be diagonal Gaussians, where you here see that the parameters in these distributions are functions of the code and the data respectively. So you obtain these parameters by pushing either the latent variables or the data through a network. And it can have the following appearance. So you input some data to your encoder network that will yield parameters for your posterior distribution that are a function of your input. You can then sample the code Z from these parameters, which you can then put into your decoder network that will yield parameters for your data likelihood. Here you have functions of your latent code, and then you will re-attain a reconstruction of the input, denoted by tilde. Now suppose we do not wish to infer the likelihood variance, but instead regard it as a hyperparameter. IA, this distribution instead have a fixed variance. Why would you want to do this? Well, adding noise to the reconstruction by sampling the x tilde doesn't add anything. So what you generally do is that you let your expected value of your likelihood be the reconstruction from your network. So that's why you don't need to waste time on inferring a parameter you do not use practically. So the practical implications of this is that we alter one part of the elbow when maximizing this entity, in addition to not inferring that parameter, and you will get the following appearance of your network. So you see here that you simply infer your expected value and not the variance here. And that is the output from your network. So how do we learn in neural networks? Well, to quantify how well a network fares, a loss function L is generally defined. And by gradient descent, we can minimize this loss function. And this can have the following appearance if we simplify things a lot. So suppose we have a two-dimensional parametric space, and that we start at some point at B0 here. You see level curves for this loss function. Then we try to find the local shape around the point we're standing, and then take a step in the direction minimizing the loss the mostly. And this is iteratively done until you find a minima. And in our VAE framework, the negative evidence lower bound is minimized. So this is analogous to maximizing the elbow. And we can decompose this into two parts, L log L and L prior, where L log L would reflect the reconstruction error between your input and output to your network, and the L prior will reflect how congruent your posterior is to the prior distribution. So by minimizing the negative elbow, we can learn the recognition model parameters and the generative model parameters simultaneously. So now suppose we have found these optimal parameters. What do we want to do with these? That's a good question. A lot of theory. Well, by characterizing our posterior distribution, we enable feature extraction on high-dimensional data, since we can map something that is potentially high-dimensional to a lower-dimensional latent space. And by characterizing our likelihood, we enable the generative process, the ability of generating new artificial data from this potentially complicated data distribution. So that's what we gain. And what can we use this for? Well, feature extraction can be applied prior to qualitative or quantitative inference, so before classification or regression, for example, or in exploratory data analysis, such as in clustering. Because when you map data to your latent space, a form of natural clustering actually occurs, so that's something you could use also. You could also use the generation of new artificial data to enable that machine learning models are better trained by balancing data sets or simply generating more data to train on. And recently an article was released that used GOMS, which I will talk about later, to balance data sets and improve classification quite much using this. So let's look at some experiments on medical images. The experiments conveyed here, they are carried out on medical patient images, and the basis for the experiment is my thesis work, which I carried out at KTH in collaboration with RaySearch, where Henrik Hult at KTH, Fredrik Laudman and Mats Holmström from RaySearch were supervising. So the data in question is computed tomography, or CT. It's generally comprised of 100 slices of dimension 512 pixels, entailing that each data sample is of dimension 10 to the power 7, so we have quite the extensive size here. And these slices are actually two-dimensional images, and if you stack them, they will give you a three-dimensional internal picture of your patient. So here is an example of a two-dimensional image, i.e. a slice of a CT scan here. This is a cross-sectional picture of the torso of a patient. And you see here the organ skin depicted. So here is the training input and output from the network. So in the top row here you have the X, and in the bottom row here you have the X tilde. And these images are of dimension 128 pixels and they are symmetric. And the latent space that this data is mapped to between these two images is only 12 dimensional. So we have put it through quite the bottleneck before reconstructing it. Here's a test input and output of a larger dimension. So these are of 256 times 256 pixels. X in the top and X tilde in the reconstruction from the network in the below row. Let's now look at the ability of generating artificial data with our decoder network. What we do here is that we sample set from our prior, we push these through our decoder network, and thus we yield artificial samples. And here are some examples. So these are two-dimensional images of dimension 256. One may also want to see a decoded interpolation in the latent space. Why would you want to do this? Well, if you sample Z1 and Z2, so 2 points from your prior distribution, and interpolate between these in your latent space, and then decode each such point, you will see how a motion in your latent space relates to a motion in your image space, and what appearance that is altered when you move. So here is an example of such a motion. So the outer two images are the initial samples, and then ones in between are the interpolated points that are all decoded. So you see a successive change from the one image into the other. The learned manifold is also something of great interest when using variational autoencoders. And in machine learning lingo, this manifold usually refers to how a higher dimensional space relates to a lower dimensional space. And this is the case here. So what you do is that you can put an equidistant grid on your latent space and then decode each point on that latent grid to see how does the image representation in the outer corner of our space looks like. And you will, by this, get a bearing on what kind of artificial samples you can generate with your decoder network. So here is an example. And proximity in this latent space will relate to how the variational autoencoder relates these images. But we still have an inference antagonist, even though we can use this in a high-dimensional case for a complicated distribution with interactabilities. In the elbow learning, we find the parameters by maximizing this entity, since direct maximization of the evidence is intractable. But recent work, the article Fixing a Broken Elbow that was presented at ICML this summer, has shown that good latent representations are actually not guaranteed. And a family of models with identical elbows can have quite different characteristics. And this supposedly stems from the fact that the posterior distribution is not influencing the loss as it should. And additionally, a strong stochastic decoder can attain a quite high elbow whilst totally ignoring the code. And what does this entail? Well, this entails that the decoder don't care where the encoder puts the latent point from a data sample. So the feature extraction where you input your data and attain a latent representation is not picked up by your second network. So the feature extraction is broken. And the authors here propose that one applies an approximation of the intractable mutual information to train on instead to mitigate this issue. And some closing remarks then. The VAE may be applied when the distribution and features of high-dimensional data is sought, but take special care regarding the feature extracting ability when applying the elbow for training. Questions?
So I have a mic here for anyone to ask a question.
You said that in a recent paper, they showed that the representation was not used to reconstruct the data. It's a bit counterintuitive for me. I wonder, how can they reconstruct the data without having information about it?
Well, I interpreted it such that it had overfitted. So it had learned that that specific part of the latent space should look like this. So if you have a very strong decoder that may be comprised of a lot of convolutional layers, that network can pick up where to map a specific point to the data space without really having any relation between the latent points and your input data. So you simply attain a too strong decoder that will win over the encoder in some kind of sense. But it's not totally intuitive. Yeah.
Have you tried other techniques of dimensional reduction?
Speak up, please. Can't hear that.
Have
I
you
could
tried
repeat the question.
other techniques?
So the question was, have you tried other techniques of dimensionality reduction?
Yeah.
Specifically on CT images?
Yeah.
Okay, so like...
Or why did you dive into this technique directly, or?
Well, the purpose was actually twofold. The dimensionality reduction was one part of it, but when you use medical data for experiments, and it's quite difficult to attain the right amount of data since you have privacy concerns and a lot of legislation. So it was mostly to see if this kind of network could generate new artificial patient data to train on. when the experiments were. So take its place.
Thanks.
Thanks. I think the mic's coming.
Did you have any like clinical applications of this? Did you use the generated images to do something cool?
Not yet, but we aim at doing it actually. There's been quite a lot to do with releases and such, so but it's something we wish to do.
Cool.
Yeah. You have a question, Brian?
Just out of curiosity, in your example, how does the set looks like? So the eggs that you will generate are just like these big slices, the tomographies, but what about the sets, the latent vectors? What are they?
They
what
are
dimensions, for example?
In these images, the latent dimension varies from a 12-dimensional latent space to a 2-dimensional latent space. So the manifold was mapped on a 2-dimensional latent space, and the other images were from 12-dimensional latent space, so quite small. And they are characterized by the Gaussian distribution, that is the prior. So that's the space it comes from.
Could you find any like interesting patterns in the latent space, like when you moved across the latent space that you showed?
Yeah, I actually showed the manifold to my dad, and he's a radiologist. So, repeat the question. Yeah, could you find any interesting patterns where the images were mapped from the data space to the image space? Oh no, data to latent space. Yes, I showed the manifold to my dad, and he could actually interpret it since he's a doctor. But it's difficult if you have an untrained eye. But if you look at, for example, the MNIST manifold, so the handwritten digits, it's easy for everyone to see that some of the images are closely related, so maybe from a 5 to a 6 and from a 2 to a 9, etc. So supposedly there are some nice things happening.
We have a final question. Okay. You're right in the back. Yeah, maybe you can repeat.
Yeah, just yell.
Your talk was very good, thank you.
Thank you.
You only explained something about variational autoencoders.
Yeah.
And I just wondered why variational autoencoders, why not just like simple, non-probabilistic autoencoders?
Well, it's because we wanted to have the generative abilities as well. So otherwise you could have used the autoencoder simply to attain the dimensionality reduction. But it was to gain the generative abilities as well. That's why we used the stochastic generalization in this case.
Cool. Thank you very much.
Thank you.
So it's time for a 15-minute break. Make sure to take some pizza, beer, and also check out the demos and the data collection by Toby. And then it's time for a second talk.